For nearly a century, a mysterious rock has been moving through space alongside Earth. It is not our moon, and it is not simply an asteroid passing by. Its orbit keeps bringing it back into the same strange relationship with our planet year after year. Scientists call it Kamoʻoalewa, and its unusual motion may reveal an even deeper story about where this tiny world came from. Before the journey begins, like the video, subscribe to the channel and join us as we uncover why this mysterious rock keeps following Earth. Kamoʻoalewa moves through the inner solar system as a small natural body whose path is governed mainly by the Sun. Although it is often described as a companion of Earth, it is not a second moon, and it does not travel around Earth in the ordinary sense. Its central motion is a solar orbit. Like Earth, it follows a curved path around the Sun, remaining part of the broad population of asteroids and planets that move under solar gravity. This simple fact establishes the largest scale of its story. The rock belongs first to the Sun's domain, and its unusual relationship with Earth exists inside that larger motion. The Sun contains almost all of the mass in the solar system, so its gravity dominates the paths of nearby planets, asteroids and comets. Earth travels around the Sun at an average distance of roughly 150 million kilometers. Kamoʻoalewa also travels at about this general distance from the Sun. Its orbit is therefore located in the same broad region as Earth's orbit, rather than deep within the asteroid belt between Mars and Jupiter. This placement gives the object a special relationship with Earth, but the shared region does not make the two bodies a gravitational pair in the same way that Earth and the Moon form a planet-moon system. A true natural satellite remains gravitationally bound to a planet. The Moon, for example, continually falls around Earth, while both Earth and the Moon together travel around the Sun. Kamoʻoalewa behaves differently. The Sun remains the main center of its orbit. Earth influences the small asteroid, but Earth does not hold it in a closed, permanent orbit like the Moon. From a broad heliocentric view, meaning a view centered on the Sun, Kamoʻoalewa and Earth are separate objects following their own solar paths. Those paths are similar in size. Earth completes one journey around the Sun in about 1 year, and Kamoʻoalewa also takes about 1 year to complete its own solar circuit. Its orbit is not identical to Earth's. It has a somewhat different shape and is tilted relative to the plane in which Earth travels. Even so, the overall size of the two paths remains close enough that the small asteroid repeatedly stays in Earth's wider orbital neighborhood. The resemblance is important because most near-Earth asteroids do not behave this way. Many cross Earth's orbital region only during certain parts of much longer or shorter solar paths. Kamoʻoalewa instead remains associated with approximately the same distance from the Sun as Earth. The asteroid's name reflects its character as a traveling companion. Kamoʻoalewa is a Hawaiian name connected with the idea of an oscillating celestial fragment. The name suits an object that appears to move with Earth over long periods while still remaining independently bound to the Sun. Its motion is quiet on the scale of the solar system. There is no continuous approach toward Earth and no simple departure into distant space. Instead, the object follows a stable pattern produced by the combined geometry of its solar orbit and the gravitational influence of nearby bodies. The surrounding environment is mostly empty space. At Earth's distance from the Sun, sunlight remains strong enough to illuminate the asteroid's surface, but the space between large bodies contains extremely little matter. Small grains of dust, charged particles from the solar wind, and occasional meteoroids occupy this region, yet the distances between substantial objects are enormous compared with their sizes. Kamoʻoalewa therefore spends nearly all of its time isolated in open space. Its nearest large gravitational influences are the Sun, and during portions of its motion Earth, while the Moon also contributes a much smaller effect. Seen from far above the plane of the planets, Earth's orbit forms a nearly circular ellipse around the Sun. Kamoʻoalewa's track lies close to that same solar distance, but is more noticeably tilted and slightly more elongated. The asteroid moves sometimes a little closer to the Sun than Earth, and sometimes a little farther away. Because its average orbital period remains close to Earth's year, these differences do not quickly separate the two objects along completely different parts of the solar system. Their motions remain linked in a broad dynamical sense even though each follows its own path. This arrangement belongs to a class of orbital behavior known as co-orbital motion. A co-orbital object shares approximately the same average orbital period as a larger planet. The term does not mean that both bodies follow exactly the same track or remain side by side. It means that their revolutions around the Sun are synchronized closely enough for the planet's gravity to shape the smaller object's long-term motion. The Sun still provides the dominant gravitational force, while the planet adds repeated smaller influences that help organize the relationship. Kamoʻoalewa is therefore best understood at this outer scale as an asteroid moving around the Sun in step with Earth. Its companionship is a result of orbital mechanics rather than a physical attachment. The small body does not need to remain close to Earth to stay associated with it. In fact, it can remain millions of kilometers away while still sharing nearly the same yearly rhythm around the Sun. Distance and companionship are not contradictory in this setting, because the connection depends on the timing and shape of solar orbits. The broad heliocentric view also removes a common visual confusion. From Earth, the asteroid's position can appear to shift in complicated loops as both objects move around the Sun. A Sun-centered view is simpler. Earth traces one orbit, Kamoʻoalewa traces another, and the two paths remain close in average size. Their relative positions change gradually because the asteroid's speed varies slightly along its orbit and because the two paths differ in shape and tilt. No hidden force is required. Ordinary gravity acting continuously over time is enough to maintain the large-scale pattern. At this scale, Kamoʻoalewa is neither a captured moon nor a wandering rock that happens to pass Earth once. It is a small solar system body whose orbit is closely matched to Earth's orbit around the Sun. The Sun governs the overall journey. Earth contributes an important but secondary gravitational influence, and the asteroid continues along a separate path within the same broad orbital region. This solar framework is the stable background against which its century-long association with Earth is understood. Earth does not travel around the Sun alone. Its orbital region contains small bodies whose paths are close enough to Earth's that the planet's gravity influences their long-term motion. These objects are called co-orbitals because they share approximately the same average orbital period as Earth. Kamoʻoalewa belongs to this unusual population. Its year around the Sun is nearly the same length as Earth's year, so the two bodies remain linked by a repeating gravitational pattern, even though they do not follow the same track through space. A one-to-one mean motion resonance describes this relationship. In orbital mechanics, a resonance occurs when two bodies complete their journeys around a larger central body in a simple repeating ratio. In this case, Earth and Kamoʻoalewa each make about one revolution around the Sun during the same interval. The small differences between their orbits cause their relative positions to change, but the overall timing remains synchronized. Earth's gravity then acts repeatedly at similar stages of the asteroid's motion, helping prevent the two objects from simply drifting apart along unrelated solar paths. The co-orbital region is not a narrow physical ring filled with closely packed rocks. It is a dynamical region created by gravity and orbital timing. Objects can occupy different positions around the Sun while still belonging to the same one-to-one resonance. Some remain near stable regions ahead of or behind a planet. Others move through broad horseshoe-shaped patterns when their motion is viewed from a frame that rotates with the planet. Kamoʻoalewa belongs to another co-orbital state known as a quasi-satellite configuration. At this scale, the important feature is that all of these forms are different expressions of the same basic relationship between orbital periods. Earth's co-orbital population is difficult to observe. Many of its members are small, faint and visible only when their positions and lighting are favorable. Their paths can also bring them into parts of the sky close to the Sun, as seen from Earth, where ordinary nighttime surveys have difficulty detecting them. As a result, the known population is probably incomplete. Kamoʻoalewa stands out because its present motion keeps it associated with Earth in a particularly persistent way, making its orbital behavior easier to recognize once enough observations are collected. The gravitational balance within this region is delicate but natural. The Sun supplies the dominant pull, setting the basic orbit of both Earth and the asteroid. Earth then adds a much weaker force that changes the asteroid's path little by little. These small changes can accumulate over many revolutions. When the timing is resonant, the changes do not occur randomly. They are organized by the repeated geometry of the two orbits. A slight shift in the asteroid's motion can alter where it meets Earth's gravitational influence during a later orbit, and that later influence can act in a way that limits the original shift. This behavior can be understood without treating the resonance as a rigid structure. There is no invisible track holding Kamoʻoalewa beside Earth. The asteroid continuously responds to gravity while moving freely through space. Its speed changes as its distance from the Sun changes, and its direction is constantly curved by solar gravity. Earth's pull slightly modifies these changes. The resulting path remains stable for a time because the asteroid occupies a region of orbital phase space where small departures are repeatedly adjusted rather than allowed to grow immediately. The shape of Earth's own orbit also matters. Earth moves on an ellipse that is close to circular, while Kamoʻoalewa follows an orbit with a somewhat greater eccentricity. Eccentricity describes how much an orbit differs from a perfect circle. The asteroid's path is also inclined to Earth's orbital plane. Inclination describes the tilt between two orbital planes. These differences mean that Kamoʻoalewa does not simply remain beside Earth at one fixed distance. Its motion carries it above and below Earth's orbital plane and through regions slightly nearer to and farther from the Sun. Because the two orbital periods are nearly equal, these differences produce a slow relative motion rather than a rapid separation. At some points, Kamoʻoalewa moves a little faster around the Sun than Earth, and at other points, it moves a little more slowly. From a Sun-centered perspective, the asteroid continues along its own ellipse. From a perspective rotating with Earth's yearly motion, however, the asteroid's position changes in a much slower and more complex way. The apparent path emerges from the combination of two solar orbits that are similar in period but different in shape and orientation. Other planets also contribute small gravitational effects. Venus, Mars, Jupiter, and the Moon can alter the asteroid's orbit over long intervals, although none dominates its present motion as strongly as the Sun and Earth. These additional influences mean that co-orbital states are not necessarily permanent. A small body can enter a resonant configuration, remain there for many decades or longer, and later move into another orbital state. The solar system is stable on large scales, yet small objects can experience gradual changes because their low masses make them more responsive to repeated planetary perturbations. Kamoʻoalewa therefore occupies a neighborhood defined less by distance than by rhythm. It is not close to Earth in the ordinary sense of a nearby moon aircraft or artificial satellite. It is close in orbital period. That matching period allows Earth's gravity to influence the asteroid in a repeated, organized way. The relationship is maintained through the combined effects of solar motion, orbital geometry, and small gravitational corrections rather than through permanent capture. Within this co-orbital neighborhood, the asteroid becomes part of a larger family of dynamical possibilities around Earth's path. Its motion shows how two objects can share nearly the same year while remaining physically separate and independently bound to the Sun. The resonance does not stop change, but it shapes change into a repeating pattern. Earth moves steadily around the Sun. Kamoʻoalewa moves on a neighboring path, and their nearly equal periods keep their motions connected across successive revolutions. The significance of this arrangement lies in its persistence. Each yearly circuit slightly reshapes the relative geometry, yet the resonance preserves a recognizable relationship between the two bodies. The asteroid remains a member of Earth's co-orbital environment because its motion continues to match Earth's even while its position, distance, and speed continually vary. Kamoʻoalewa's distinctive motion appears when its path is viewed from a frame that moves around the Sun with Earth. In this rotating perspective, Earth remains at the center, while the asteroid seems to trace a looping pattern around it. This appearance gives rise to the term quasi-satellite. The word describes an object that seems to accompany a planet in orbital rhythm without becoming a true gravitationally bound moon. From a sun-centered perspective, Kamoʻoalewa continues to orbit the Sun. From Earth's rotating perspective, however, the differences between the two solar orbits appear as a slow, relative motion. Because the asteroid's year is almost the same length as Earth's year, it does not rapidly drift across the sky. Instead, its position shifts gradually, producing a repeated loop that can resemble a loose orbit around Earth. The apparent loop is created by geometry rather than by capture. Kamoʻoalewa moves on an orbit that is more elongated and tilted than Earth's. At parts of its path, it moves closer to the Sun and travels slightly faster. At other parts, it lies farther from the Sun and moves slightly more slowly. These changes alter its position relative to Earth. Over time, the asteroid appears to move ahead, fall behind, rise above, and pass below the plane of Earth's orbit. The resulting pattern is much larger than the orbit of the Moon. Kamoʻoalewa remains millions of kilometers from Earth through much of its motion. It never circles the planet in the compact way expected of a natural satellite. The Sun still dominates the asteroid's acceleration throughout. Earth's gravity modifies the path enough to organize the relative motion, but not enough to remove the asteroid from its solar orbit. This distinction is important because the word satellite can suggest something permanently attached to a planet. A quasi-satellite is different. Its apparent companionship depends on resonance and perspective. If Earth's motion around the Sun were removed from the reference frame, the loop would disappear, leaving two nearby heliocentric orbits instead. The looping pattern, therefore, represents relative motion between bodies that share nearly the same orbital period. The shape of the loop changes gradually because planetary gravity never acts in complete isolation. Earth provides the strongest nearby perturbation, while the Moon and other planets add smaller influences. These forces slightly alter the asteroid's orbital elements over time. Orbital elements are the quantities used to describe the size, shape, tilt, and orientation of an orbit. Small changes in these values shift the appearance of the quasi-satellite path from one year to another. Even with these changes, the broad pattern remains recognizable over many revolutions. The asteroid alternates between portions of its motion where it appears to advance relative to Earth and portions where it appears to retreat. Because the orbit is inclined, the apparent loop also contains a vertical component when compared with Earth's orbital plane. The result is a three-dimensional path rather than a flat circle. Computer calculations are useful for studying this motion. Astronomers combine repeated measurements of the asteroid's position with gravitational models of the solar system. The calculated trajectory can then be followed forward and backward in time. These models show how the asteroid's relative position develops from the laws of motion and gravity. No additional mechanism is needed to explain the repeated companionship. Kamoʻoalewa's path also demonstrates why visual appearance alone can be misleading in orbital astronomy. A body can seem to circle a planet without actually being bound to it. The same coordinates can look very different depending on whether the observer uses a sun-centered frame or a frame rotating with Earth. Both descriptions are valid, but they answer different questions. The sun-centered view reveals what the asteroid orbits. The rotating view reveals how its motion stays organized relative to Earth. Within this moving frame, Kamoʻoalewa appears to remain nearby because its average motion around the Sun matches Earth's. The loop is therefore not a separate orbit superimposed on its solar path. It is the visual form of the resonance itself expressed through relative motion. The asteroid continues around the Sun, Earth continues around the Sun, and the small differences between their paths combine into a slow, repeating pattern around the planet's position. Kamoʻoalewa's present quasi-satellite state is not only unusual in shape, it is also persistent across human time scales. Orbital calculations indicate that the asteroid has remained in this general configuration for close to a century. During that interval, Earth's gravity repeatedly alters its relative motion enough to keep the small body from drifting quickly away along its solar orbit. The pattern can be understood as a sequence of slow corrections. When Kamoʻoalewa moves slightly ahead of Earth in its shared journey around the Sun, the geometry of their positions changes the way Earth's gravity acts on it. When the asteroid later falls behind, the direction and timing of that influence change again. These repeated interactions do not lock the object in place, but they help maintain the broad quasi-satellite pattern. The effect is subtle because the asteroid remains far from Earth compared with the Moon. Earth does not dominate its motion. The Sun continues to provide the main gravitational force, while Earth contributes smaller perturbations that accumulate over time. A perturbation is a small change in an orbit caused by the gravity of another body. In Kamoʻoalewa's case, these perturbations are organized by the one-to-one resonance already established between the asteroid and Earth. Over decades, the asteroid's relative position shifts through a repeating cycle. It can appear to move forward in relation to Earth, slow reverse direction in the rotating frame, and then return through another part of the loop. The motion is continuous rather than sudden. Each change grows from the combined effects of orbital speed distance from the Sun inclination and Earth's repeated gravitational pull. Backward integrations of the orbit help astronomers estimate how long this state has lasted. These calculations begin with the asteroid's measured position and velocity, and then apply the gravitational influence of the Sun, planets, and Moon in reverse through time. Because every observation contains some uncertainty, the farther backward the calculation extends, the wider the range of possible past paths becomes. Even so, the results support a quasi-satellite configuration extending through roughly the last 100 years. This does not mean that the asteroid has occupied exactly the same loop for every year of that interval. The shape and orientation of its relative path change gradually. Planetary perturbations modify the orbit, and the Moon adds smaller corrections as Earth and the Moon move together around their common center of mass. The system remains dynamic, with stability arising from repeated adjustments rather than from a perfectly fixed track. The same principle applies when calculations are carried forward. Kamoʻoalewa is expected to remain associated with Earth for a substantial period, but the precise duration depends on the details of its evolving orbit. Small uncertainties become more important over long spans, especially when gravitational encounters alter orbital elements slightly. Its current state is therefore stable on the scale of decades and centuries, without being permanent on the scale of solar system history. The phrase "following Earth" is useful only when understood in this dynamical sense. Kamoʻoalewa does not trail directly behind the planet like an object attached to it. Its distance and direction change throughout each cycle. Sometimes it lies on one side of Earth's position around the Sun, and later it occupies another. What persists is not a fixed location, but a relationship between two orbital rhythms. This persistence also separates the present orbit from a simple flyby. A passing asteroid normally approaches, crosses Earth's neighborhood, and continues onto a path that carries it away. Kamoʻoalewa instead returns to a similar dynamical relationship after each revolution. The repeated pattern allows astronomers to identify continuity across generations of observations and reconstructed motion. Its century of companionship is therefore not measured by physical closeness, but by the survival of the resonant arrangement through many journeys around the Sun. This century-long behavior shows how gravity can produce order without capture. The asteroid remains free to orbit the Sun, yet Earth's repeated influence limits its long-term drift. The result is a companion that stays within the same broad orbital neighborhood while continually changing its position. Its apparent loyalty to Earth is therefore an outcome of resonance timing and small gravitational corrections acting steadily across many revolutions around the Sun. Kamoʻoalewa becomes known to astronomy through careful observation rather than a close encounter with Earth. The object is first identified in 2016 by the Pan-STARRS survey in Hawaii. Pan-STARRS uses wide-field telescopes to photograph areas of the night sky, searching for objects whose positions change against the distant background of stars. A faint point of light that shifts between images can reveal an asteroid even when the object itself is far too small to be seen as a resolved world. The discovery process begins with position. Astronomers record where the moving point appears on the sky at precise times. A single observation cannot determine a complete orbit because many different paths can pass through the same apparent position. Additional measurements taken later show how quickly the object moves and how its direction changes. Each position reduces the range of possible trajectories. The result is called an observational arc, meaning the span of time over which the object has been measured. For Kamoʻoalewa, the first observations reveal that its motion is unusual. Its apparent movement does not match that of a distant main belt asteroid, and it does not behave like a body making a simple passage near Earth. As more measurements accumulate, astronomers calculate a preliminary orbit around the Sun. The estimated orbital period turns out to be close to 1 Earth year. That result is important because objects with nearly the same period as Earth can enter one-to-one resonant states. Orbit determination depends on both observation and physics. The measured positions are compared with mathematical models of motion under gravity. The Sun provides the dominant force, while Earth, the Moon, and the other planets add smaller influences. Computers adjust the asteroid's estimated position and velocity until the calculated path agrees as closely as possible with the recorded observations. The solution provides orbital elements that describe the size, shape, tilt, and orientation of the path. Uncertainty remains part of this process. Every telescope measurement has limited precision, and a faint asteroid can be especially difficult to locate exactly. Atmospheric conditions, image quality, and the brightness of the object can affect the measurement. Astronomers, therefore, do not treat an orbit as a perfectly known line. They calculate a range of possible solutions consistent with the available data. As the observational arc grows longer, that range usually becomes narrower. Repeated observations of Kamoʻoalewa strengthen the orbital solution. Measurements taken during later observing opportunities extend the time baseline and show that the asteroid returns to positions predicted by the resonant model. The longer record makes it possible to distinguish temporary similarities from persistent orbital behavior. Its relationship with Earth becomes clear not from one dramatic image, but from many measurements collected over time. Archival observations can also improve an orbit. Once an asteroid is discovered and its approximate path is known, astronomers can search older survey images taken before the official discovery date. A faint point that was not recognized at the time may be found at the position predicted by new calculations. Such pre-discovery detections extend the observational arc backward and give the orbital model additional leverage. The asteroid's faintness makes this work demanding. Kamoʻoalewa is small and reflects only a limited amount of sunlight. Its visibility changes as the geometry among the Sun, Earth, and asteroid changes. During favorable periods, telescopes can gather enough light to measure its position accurately. During less favorable periods, it becomes difficult or impossible to observe from the ground. By combining these measurements, astronomers reconstruct the path that Kamoʻoalewa follows around the Sun and its changing position relative to Earth. The orbit is not inferred from appearance alone. It emerges from repeated coordinates, precise timing, gravitational calculations, and statistical estimates of uncertainty. The process turns a faint moving point into a body with a measurable dynamical history. Kamoʻoalewa's discovery, therefore, illustrates how modern asteroid astronomy often works. A small object first appears as a subtle displacement among stars. Continued observation gives that displacement a speed and direction. A longer sequence reveals an orbit. In this case, the reconstructed orbit shows that the asteroid is not merely passing through Earth's neighborhood, but occupies a persistent co-orbital relationship that can be followed through calculation and observation. Kamoʻoalewa remains a difficult object to study because its physical scale is extremely small compared with the distances separating it from Earth. Although its orbital relationship makes it a companion in a dynamical sense, it usually stays many millions of kilometers away. Calculations indicate it does not approach much closer than roughly 38 times the average distance between Earth and the Moon, and it can move outward to about 100 lunar distances. These separations keep it well beyond the region occupied by artificial satellites and far outside the Moon's orbit. At such distances, the asteroid appears only as a point of light through ground-based telescopes. Its surface cannot normally be resolved into mountains, craters, or boulders. Astronomers estimate its physical properties indirectly from the amount of sunlight it reflects and from changes in that reflected light over time. The task is complicated because brightness depends on several factors, including the asteroid's size, its distance from the observer, its distance from the Sun, and the fraction of incoming sunlight that its surface reflects. The fraction of light reflected by a surface is described by its albedo. A dark object and a bright object of the same size can produce very different signals at a telescope. Without a direct measurement of Kamoʻoalewa's albedo, its diameter cannot be determined precisely from brightness alone. Early estimates placed its size broadly between about 40 and 100 meters. Later, spectral studies using plausible surface reflectivities have favored values of roughly several tens of meters with estimates near 50 meters in models. This means that the asteroid is comparable in length to a modest building Rather than to a mountain or a large planetary moon, its tiny dimensions help explain why it remained undiscovered until wide-field surveys became sensitive enough to detect very faint moving sources. Even when its position in the sky is favorable, the amount of sunlight intercepted by such a small body is limited. Only a small fraction of that light is reflected toward Earth, and that reflected signal spreads across immense distance before reaching a telescope. Brightness changes as the viewing geometry changes. When the asteroid lies in a position where a larger part of its illuminated surface faces Earth, it appears brighter. When the geometry is less favorable, the observed signal weakens. Its changing distance adds another variation. Light reflected from a more distant position becomes harder to collect. So useful observing opportunities are concentrated into limited periods rather than distributed evenly through every year. The night sky itself creates additional limits. An asteroid may be present above the horizon but still be difficult to measure. If it lies near the apparent direction of the sun, passes through bright moonlight, or remains low in the atmosphere, ground-based observations work best when the object appears against a dark sky and spends enough time above the horizon for instruments to gather repeated exposures. For Kamoʻoalewa, favorable windows can be brief because the same orbital geometry that keeps it associated with Earth also restricts where it appears in the sky. Large telescopes improve these measurements by collecting more photons, the individual packets of light detected by astronomical instruments. More collected light allows astronomers to determine brightness with greater precision and, under suitable conditions, separate that light into a spectrum. Yet even powerful telescopes face fundamental limits when the source is both small and distant. Kamoʻoalewa remains unresolved, so almost everything known about its physical form must be inferred from integrated light coming from the entire visible surface. Its faintness, therefore, shapes the kind of science that can be performed. Astronomers can determine an accurate orbit from repeated positional measurements and can estimate broad physical properties from brightness. They can also study changes in the light as the asteroid turns. Direct knowledge of its exact dimensions and detailed landscape, however, remains more limited than for larger asteroids visited by spacecraft or observed closely by radar. At this physical scale, Kamoʻoalewa is a very small rock moving across a very large volume of space. Its companionship with Earth does not make it visually prominent. The asteroid remains distant, faint and unresolved, and its size must be reconstructed from sparse light gathered across millions of kilometers. Kamoʻoalewa does not remain still as it travels around the Sun. Like most small asteroids, it rotates, and this spin changes how much of its irregular surface reflects sunlight toward Earth. Astronomers detect the rotation through repeated brightness measurements as different sides of the body turn into view. The amount of reflected light rises and falls in a repeating pattern. This pattern is called a light curve, and it provides one of the few ways to study the motion of an object too small and distant to resolve directly. Measurements indicate that Kamoʻoalewa rotates very quickly. Its rotation period is roughly 28 minutes, meaning that it completes a full turn in less than half an hour. This is rapid compared with many larger asteroids, which can take several hours to rotate once. The short period immediately places Kamoʻoalewa in a category where internal strength becomes important, because a loosely bound collection of fragments can have difficulty remaining intact when it spins too fast. For larger rubble pile asteroids, gravity helps hold separate blocks and grains together. There is a practical spin limit near a few hours for many such bodies, because faster rotation can cause loose surface material to shift outward or escape. Kamoʻoalewa is much smaller, however, so its structure may not behave like that of a large gravitational aggregate. At scales of only several tens of meters, cohesive forces between particles and the mechanical strength of solid rock can become more important than self-gravity. The fast rotation, therefore, offers a clue about the asteroid's internal nature, but it does not provide a complete answer. A compact, monolithic fragment could survive rapid spinning because the rock itself supplies the needed strength. A smaller aggregate with enough cohesion between grains might also remain stable. Current observations do not directly reveal the internal arrangement, so the rotation period constrains possible structures without uniquely determining one. The light curve also carries information about shape. A perfectly spherical object with uniform surface brightness would show little change as it turns. Kamoʻoalewa displays measurable variations which indicate that its visible cross-section or surface reflectivity changes during rotation. This suggests that the body is not a perfect sphere. It may be elongated, irregular, or covered with regions that reflect different amounts of sunlight. Because the asteroid remains unresolved, these possibilities are inferred from the rhythm and amplitude of the changing light, rather than from direct images of its outline. The orientation of the spin axis also affects what telescopes observe. If the axis points close to the observer, only limited changes in projected shape may be visible. If the axis lies more nearly sideways, larger brightness variations can appear as broad and narrow sides rotate into view. The viewing geometry changes as Earth and the asteroid move around the Sun, so observations taken at different times can provide additional constraints. Even then, uncertainty remains because several combinations of shape, surface, texture, and spin orientation can produce similar light curves. Rapid rotation also changes conditions across the surface. Daylight and darkness alternate every few minutes rather than over many hours. Sunlit areas warm, then move quickly into shadow and begin cooling. On a small airless body, there is no atmosphere to spread heat efficiently from one region to another. The temperature of the uppermost surface therefore responds directly to the changing illumination, although the deeper material changes more slowly. This repeated cycle does not mean the entire asteroid heats and cools uniformly. Surface rocks, dust, and exposed mineral grains can respond differently depending on their size, density, and thermal properties. The rotation sets the timing of these changes while sunlight provides the energy. Measurements of thermal behavior can therefore complement visible light observations when sufficient data are available. Kamoʻoalewa's 28-minute spin is one of its clearest measured physical characteristics. It turns a distant point of light into a body with a detectable rhythm. Each rise and fall in brightness reflects motion at the surface scale, revealing that the asteroid is small, irregular, and rapidly rotating while it continues along its solar orbit. The repeating signal gives astronomers a steady observational clock, allowing separate nights of data to be compared through the same rapid cycle of rotation itself. Sunlight provides the main source of information about Kamoʻoalewa's surface. The asteroid does not produce light of its own. Instead, sunlight strikes its exposed material, and a small fraction of that light is reflected back into space. Some of the reflected light reaches telescopes on Earth. By measuring how strongly the asteroid reflects different wavelengths, astronomers can study properties of the surface even though the body itself remains too small to resolve. The reflected signal changes with wavelength because minerals do not interact with all parts of sunlight. In the same way, some wavelengths are reflected efficiently, while others are partly absorbed by atoms and crystal structures within the surface material. When the light is separated into a spectrum, these differences appear as gradual slopes and shallow absorption features. A spectrum, therefore, acts as a remote measurement of surface composition rather than as a direct image of individual rocks. Observations of Kamoʻoalewa show that its spectrum is noticeably red. In this context, red does not mean that the asteroid would necessarily appear bright red to the human eye. It means that the surface reflects relatively more light at longer visible and near-infrared wavelengths than at shorter wavelengths. This rising spectral slope is stronger than the slopes measured for many near-Earth asteroids, and becomes one of the characteristics that makes Kamoʻoalewa unusual. The surface brightness is also affected by the angle of illumination. An airless asteroid has no atmosphere to scatter sunlight evenly across its visible face. Brightness depends directly on which areas receive sunlight and which remain in shadow. Rough terrain can contain slopes, grains, cracks, and cavities. Each surface element reflects light differently, depending on its orientation toward the sun and the observer. The combined signal represents light from all of these unresolved regions at once. Kamoʻoalewa's rapid rotation adds another layer of variation. During a single observing session, portions of the surface can rotate into view. If the asteroid is elongated, its projected area changes during each turn. If some regions are brighter or darker than others, those differences also influence the measured light. Astronomers, therefore, take repeated measurements across rotation phases so that temporary brightness changes can be separated from the broader spectral shape. The reflected signal remains limited. Kamoʻoalewa intercepts only a small amount of sunlight because its surface area is tiny compared with that of a planet or large asteroid. The reflected light then travels millions of kilometers before reaching Earth. Instruments must collect enough photons across each wavelength range to distinguish a genuine surface pattern from measurement noise. Favorable observing conditions are therefore essential, particularly for near-infrared measurements. Researchers combine observations from different wavelength regions to build a complete spectrum. Visible light records one portion of the surface response, while near-infrared light extends the measurement into wavelengths where important rocky minerals often produce absorption features. The combined spectrum does not identify every mineral independently, but it can be compared with spectra measured from meteorites, lunar samples, laboratory minerals, and other asteroids. These comparisons require caution. Different materials can sometimes produce similar broad spectral shapes, especially after their surfaces have been altered by long exposure to space. Grain size, temperature, viewing geometry, and mixtures of minerals can also change the appearance of a spectrum. Reflected light, therefore, usually narrows the range of plausible materials rather than providing a complete chemical description. Even with these limits, Kamoʻoalewa's reflected sunlight contains more information than its faint appearance suggests. The spectrum records how the uppermost layer of the asteroid interacts with solar radiation. Its red slope, changing brightness, and wavelength-dependent absorption all arise from physical conditions at the surface. Each measurement remains indirect, yet together they allow astronomers to move from the asteroid's size and rotation toward the composition of material exposed on its exterior. At this scale, the asteroid is no longer only a moving point whose position can be tracked against the stars. Its light carries a measurable signature of the surface itself. Sunlight leaves the sun, reaches Kamoʻoalewa, interacts with mineral grains, and returns toward Earth, carrying subtle changes. Those changes provide the observational bridge between the asteroid's motion through space and the physical nature of the rock that produces the reflected signal. The spectrum of Kamoʻoalewa contains a broad absorption feature near a wavelength of about 1 micrometer. This region of the spectrum is especially useful for studying rocky surfaces because several common silicate minerals absorb sunlight there. Silicates are minerals built mainly from silicon and oxygen combined with elements such as magnesium, iron, and calcium. They form much of the rocky material found in planets, moons, meteorites, and asteroids throughout the inner solar system. The presence of this absorption feature indicates that Kamoʻoalewa is not composed mainly of exposed metal or volatile ice. Its surface is dominated by rocky material containing minerals related to olivine, pyroxene, or mixtures of both. Olivine and pyroxene are common silicates in planetary crusts and primitive rocky bodies. Their crystal structures absorb particular wavelengths of near-infrared light, leaving broad depressions in a reflected spectrum. The exact shape of an absorption band depends on composition. Iron content, magnesium content, mineral, proportions, grain size, and surface alteration can all shift or reshape the feature. Astronomers therefore compare Kamoʻoalewa's spectrum with laboratory measurements of known materials. These include meteorite samples, terrestrial minerals, lunar rocks, and spectra measured directly from other airless bodies. A close match can identify broad
mineral families, although it cannot always establish a unique source.
Kamoʻoalewa's spectral feature is accompanied by its strongly red overall slope. This combination makes interpretation more difficult. A fresh mineral surface may reflect light differently after long exposure to the environment of space. As a result, a direct comparison with newly broken laboratory rock can be misleading. Researchers must consider both the mineral absorption and the condition of the surface grains producing it. The available observations indicate a silicate-rich body, but they do not provide a complete mineral inventory. The asteroid is too faint for the same detailed spectroscopy available for the Moon or large asteroids. Some absorption bands remain weak, uncertain, or outside the most useful observing conditions. Atmospheric water vapor above ground-based telescopes can also interfere with particular infrared wavelengths, reducing the quality of parts of the spectrum. Even so, the broad mineral signal is consistent across the observations used to characterize the asteroid. Rocky silicates provide a natural explanation for the measured absorption. The spectrum, therefore, places Kamoʻoalewa among solid rocky objects rather than among icy, comet-like bodies. This conclusion fits its location in the warm inner solar system where exposed volatile materials are difficult to preserve near the surface over long periods. The minerals themselves are not unusual on a cosmic scale. Olivine and pyroxene appear in many meteorites and on numerous asteroids. They are also abundant in lunar rocks. Their presence alone, therefore, cannot determine where Kamoʻoalewa formed. The value of the spectrum comes from the detailed combination of mineral absorption, overall slope, and the degree to which the surface appears altered. Each photon reflected from the asteroid interacts only with the uppermost portion of the surface. Spectroscopy, therefore, measures a thin optical layer rather than the deep interior. Dust-fractured rock and exposed grains can dominate the signal even if the material beneath them differs in texture. Impacts and temperature cycling can continually expose or rearrange small amounts of material, but the observed spectrum remains weighted toward what is presently visible at the surface. The 1 micrometer feature nevertheless provides a firm step inward from brightness alone. Brightness reveals how much light the asteroid returns, while spectroscopy reveals which wavelengths are removed more efficiently. Those missing wavelengths contain information about chemical bonds and crystal structures within the surface minerals. At this scale, Kamoʻoalewa becomes more than a faint object, with a measured orbit and rapid spin. Its reflected light shows that the exterior is made of silicate-bearing rock. The precise mixture remains uncertain, but the mineral signature establishes a physical connection with the widespread rocky materials of the inner solar system. Kamoʻoalewa's surface does not remain optically unchanged while it travels through space. It is exposed directly to sunlight, energetic particles, and a continual rain of tiny impacts. These processes gradually alter the outermost mineral grains. The collective change is known as space weathering. It affects how a surface reflects light without necessarily changing the basic minerals from which the rock is made. On Earth, weathering is usually driven by water atmosphere and temperature changes. Kamoʻoalewa has no substantial atmosphere. Its weathering environment is therefore different. Solar radiation reaches the ground without atmospheric filtering. The solar wind, a stream of charged particles flowing outward from the sun, strikes exposed grains directly. Micrometeoroids also collide with the surface, delivering brief pulses of heat and disruption. Over long periods, these effects can modify the uppermost layers of mineral particles. Tiny impacts can melt or vaporize amounts of material and redeposit them nearby. Charged particles can damage crystal structures and alter the chemistry of grain surfaces. In some rocky materials, microscopic particles of metallic iron can form within or around weathered grains. These changes influence the way light is scattered and absorbed. One common optical result is a darker and redder spectrum. A weathered surface may reflect less total light while reflecting proportionally more at longer wavelengths. Absorption features can also become weaker. The exact response depends on the original minerals, the length and intensity of exposure, and the physical character of the surface. Space weathering, therefore, does not produce one universal spectral pattern, but it can substantially alter the appearance of rock. Kamoʻoalewa's unusually red spectral slope has made this process important in attempts to interpret its composition. A fresh terrestrial sample of olivine or pyroxene may not resemble the asteroid when measured in a laboratory. If that sample is compared with material that has spent long periods exposed on the Moon or another airless body, the match can change. Researchers therefore consider mineral composition and surface maturity when comparing spectra. The term surface maturity describes the degree to which exposed material has been altered by prolonged space weathering. Fresh material can be created when an impact breaks a rock and reveals an interior surface. Mature material has spent longer in direct contact with the space environment. On the Moon, these differences are measurable because young impact ejecta can appear optically distinct from older surrounding soil. Similar principles may apply to a small asteroid, although its low gravity and rapid rotation produce a different physical environment. Kamoʻoalewa's small size means that material disturbed by impacts can escape more easily than it does from the Moon. Some fragments may leave the asteroid entirely because the gravitational pull is weak. Other grains may remain attached through contact forces or settle into small depressions. Its rapid rotation also changes the direction and strength of effective surface gravity across the body. These factors influence how long weathered grains remain exposed and how often fresh material appears. Thermal cycling contributes additional stress. As the asteroid rotates, surface regions move repeatedly between sunlight and darkness. Minerals expand when warmed and contract when cooled. Repeated cycles can create small fractures in exposed rocks, eventually breaking larger pieces into smaller fragments. This process changes texture and grain size, which in turn can affect reflected light. It operates alongside particle irradiation and micrometeoroid impacts rather than replacing them. Spectral observations cannot measure the age of surface grains directly. They show only the combined optical behavior of the visible surface. A very red slope can be consistent with strong weathering, but the exact exposure, history remains uncertain because composition and grain structure also influence color. Researchers, therefore, avoid treating redness alone as proof of a particular origin. At this scale, Kamoʻoalewa's exterior is understood as an optical boundary, shaped by the space environment. The underlying rock may retain familiar silicate minerals while the surfaces of its grains acquire damage, coatings, fractures, and microscopic chemical changes. The light returning to Earth carries the signature of both the original material and this accumulated alteration. Space weathering, therefore, becomes essential for reading the asteroid's spectrum correctly, because the surface seen by telescopes is not simply fresh rock, but rock transformed by prolonged exposure in near-Earth space. Kamoʻoalewa's surface spectrum becomes especially interesting when it is compared with material from the Moon. Observations indicate that the asteroid reflects sunlight in a way that differs from many ordinary near-Earth asteroids. Its broad, silicate absorption and strongly red spectral slope resemble the optical behavior of lunar material that has been exposed to the space environment for long periods. This similarity has led researchers to consider the possibility that Kamoʻoalewa may contain rock that once formed part of the Moon. The comparison does not depend on color alone. Scientists examine the shape of the spectrum across visible and near-infrared wavelengths, including the position and depth of the broad absorption associated with silicate minerals. Lunar samples and remotely measured lunar surfaces provide a large reference collection because the Moon contains abundant olivine pyroxene feldspar and related rocky minerals. Many of these materials develop altered optical properties after prolonged exposure to solar wind and micrometeoroid impacts. Kamoʻoalewa's spectrum appears unusually red compared with many asteroids classified within common rocky groups. When researchers compare it with fresh meteorite samples, the match is limited. When they compare it with mature lunar surfaces and weathered lunar material, the resemblance becomes stronger. This result is important because it suggests that both mineral composition and surface alteration may contribute to the asteroid's observed light. A lunar interpretation also fits the general idea of an airless, rocky fragment. The Moon has no dense atmosphere, so exposed material experiences space weathering directly. Small fragments created by large impacts can inherit the mineral composition of the lunar crust while later developing their own weathered surfaces during travel through space. Kamoʻoalewa's spectrum is therefore consistent with material that could have begun as lunar rock and then continued to change after separation. Consistency, however, is not the same as proof. Spectroscopy measures reflected light from the surface and cannot identify a birthplace directly. Different rocky materials can produce overlapping spectral patterns, especially after their grain size, surface chemistry, and exposure history change. A strongly weathered asteroid containing certain silicates could potentially resemble lunar material without ever having been part of the Moon. The uncertainties are increased by the faintness of Kamoʻoalewa. Its spectrum is assembled from difficult observations of a very small object at great distance. Noise affects the exact slope and depth of absorption features. Different observing nights can also involve different viewing geometries and different portions of the rotating surface. Researchers, therefore, compare broad patterns rather than treating every small spectral variation as a firm compositional difference. Lunar rocks themselves are not uniform. The Moon contains ancient highland crust. Darker volcanic plains impact melt fragmented breccias and soils mixed by billions of years of bombardment. Their spectra vary according to composition and exposure. A resemblance between Kamoʻoalewa and lunar material does not therefore identify one exact lunar rock type or one precise location on the Moon. The strength of the lunar hypothesis comes from the combination of several broad properties rather than from a single spectral feature. Kamoʻoalewa is a small silicate-rich object. Its surface appears strongly weathered and its reflectance resembles mature lunar material more closely than many common asteroid examples used in early comparisons. These observations make a lunar origin scientifically plausible. At the same time, the interpretation remains conditional. The spectrum describes the surface that is visible now, not necessarily the entire interior. Weathering can alter optical properties enough to obscure the original appearance of the material. Limited wavelength coverage can leave alternative compositions unresolved. The available observations, therefore, support a lunar connection without uniquely establishing one. At this material scale, Kamoʻoalewa carries a surface signature that can be compared with rocks already studied in laboratories and across the Moon. The resemblance is close enough to change the scientific discussion from simple classification toward possible origin. The measured light indicates silicate minerals altered by prolonged exposure, and lunar material provides one strong physical match. The evidence remains suggestive rather than final, preserving a clear distinction between what the spectrum shows and what its birthplace may have been. For now, the lunar comparison remains an interpretation built from reflected light mineral behavior and surface alteration, with each element contributing evidence while leaving room for another rocky source elsewhere. Kamoʻoalewa's possible lunar origin requires more than a spectral resemblance. A fragment of the moon must also be able to escape lunar gravity, move through the gravitational environment of Earth and the Moon, and enter a solar orbit similar to Earth's. Numerical studies show that such a pathway exists, although it is uncommon. The process begins when a sufficiently energetic impact strikes the lunar surface and accelerates pieces of rock away from the impact site. The Moon's escape speed is a little more than 2 kilometers per second. Material launched below that speed eventually falls back unless later interactions change its motion. Faster ejector can leave the Moon, but escaping the Moon alone does not guarantee escape from the wider Earth-Moon system. Earth's gravity continues to influence the fragment after it has moved beyond the immediate lunar environment. To become an independent heliocentric object, the fragment must retain enough energy and a suitable direction to pass outward from this combined gravitational region. The launch direction matters because the Moon is already moving around Earth. A fragment ejected in one direction can add to that orbital motion, while a fragment launched in another direction can partly subtract from it. This changes the speed the fragment has relative to Earth after leaving the Moon. Simulations find that launches from the Moon's trailing hemisphere can be especially favorable for producing Earth-like solar orbits. The trailing hemisphere faces generally opposite the Moon's direction of travel around Earth. Once a fragment escapes the Earth-Moon region, the Sun becomes the dominant body, controlling its trajectory. The fragment then enters a heliocentric orbit with a speed that differs only slightly from Earth's orbital speed. If the escape conditions are favorable, small differences are important. A large velocity difference tends to send the fragment onto a noticeably different orbit, while a smaller residual difference can leave it traveling near the same average solar distance as Earth. This is where a dynamical difficulty appears. Most lunar ejecta that reach heliocentric space do not settle into Earth's co-orbital region. Simulations of thousands of test particles show that the majority move into ordinary near-Earth asteroid paths. Only a small fraction enter temporary co-orbital motion. An even smaller subset develops behavior resembling the alternating quasi-satellite and horseshoe states associated with Kamoʻoalewa. The rarity of these outcomes does not make the pathway impossible. Large impacts can produce enormous numbers of fragments with different speeds, directions, and sizes. Even when favorable trajectories represent only a small fraction of possible launches, some pieces can occupy them. Numerical models therefore test whether physically reasonable impacts can populate the required part of orbital space, rather than assuming that every lunar fragment should behave in the same way. The successful simulated cases tend to begin with launch speeds only moderately above the values needed for escape. If a fragment leaves with too much excess speed, its new solar orbit becomes less similar to Earth's. When the residual velocity remains small, the fragment starts its independent solar journey, close to Earth's orbital energy. Planetary perturbations can then shape the orbit further and occasionally guide the fragment into a one-to-one resonance. These calculations are sensitive to initial conditions. Tiny changes in launch angle or speed can lead to very different outcomes after repeated encounters and solar revolutions. The motion is therefore described statistically rather than as one unique route that every fragment follows. Researchers model many possible particles and examine how often Kamoʻoalewa-like behavior emerges. The simulations establish a physical connection between lunar impacts and Earth co-orbitals. They do not establish that Kamoʻoalewa itself definitely follows this history. What they show is that lunar rock can leave the Moon, escape the Earth-Moon system, enter a heliocentric orbit, and under rare conditions evolve into the same broad, dynamical class occupied by Kamoʻoalewa. The proposed lunar origin is therefore compatible with known gravitational mechanics rather than requiring an unexplained process. At each stage, ordinary gravity supplies the necessary changes. The impact provides the initial speed the Moon and Earth reshape the departing trajectory, and the Sun establishes the orbit. No permanent gravitational capture is required. The pathway is narrow but repeated. Lunar impacts over geological time provide many opportunities for suitable fragments. Among the possible lunar source regions, one young impact crater has received particular attention. Giordano Bruno lies on the far side of the Moon close to the northeastern edge of the lunar disk as seen from Earth. The crater is about 22 kilometers across and is considered geologically young compared with most large lunar craters. Estimates place its formation within roughly the last 1 to 10 million years, although its exact age remains uncertain. This age range matters because a fragment the size of Kamoʻoalewa cannot remain indefinitely on an Earth-like orbit without its path changing. Numerical studies indicate that a lunar fragment reaching the present co-orbital state is more consistent with a relatively recent impact than with an event dating back billions of years. A young crater, therefore, provides a more suitable source than the ancient basins that dominate much of the lunar surface. Researchers examine whether an impact capable of forming Giordano Bruno can launch fragments large enough to survive escape from the Moon. Impact simulations show that a crater tens of kilometers wide can eject some blocks with dimensions of several tens of meters or more. Most ejecta do not escape. Much of the material lands again on the Moon, while other fragments leave on trajectories that do not resemble Kamoʻoalewa's present orbit. A small fraction, however, can depart with suitable speeds and directions. The location of Giordano Bruno also contributes to the hypothesis. Its position on the lunar surface allows some ejecta to leave with velocity conditions that can favor escape into heliocentric space. After leaving the Moon, a successful fragment must pass through Earth's gravitational influence without colliding with Earth or returning to the Moon. It must then acquire a solar orbit with an average distance and period close to Earth's. Researchers model this chain with two connected kinds of simulation. Impact calculations estimate the sizes and velocities of fragments produced when an incoming asteroid strikes the lunar crust. Gravitational calculations then follow representative fragments after launch, tracking their movement through the Earth-Moon system and around the Sun. The combined approach tests whether a physically realistic crater-forming event can produce both a Kamoʻoalewa-sized fragment and a Kamoʻoalewa-like orbit. The results, published in 2024, find that these requirements can be satisfied under plausible conditions. Craters larger than roughly 10 to 20 kilometers can produce sufficiently large escaping fragments, and some simulated trajectories enter Earth's one-to-one resonance. Giordano Bruno stands out because its diameter, young estimated age, and location satisfy several of the constraints at the same time. This does not establish a direct historical link. No observation currently traces Kamoʻoalewa backward to the moment Giordano Bruno forms. Over millions of years, small gravitational differences grow, and precise reconstruction of a single fragment's path becomes impossible. The crater age itself also spans a substantial interval. The connection is therefore probabilistic rather than a recovered trajectory. The physical composition provides another limitation. Remote spectroscopy indicates that Kamoʻoalewa resembles weathered lunar silicate material, but that resemblance does not identify Giordano Bruno specifically. Different parts of the Moon contain overlapping mineral components, and space weathering changes the surfaces of both lunar rocks and small fragments. A match to lunar material can support a lunar origin without selecting one crater with certainty. The hypothesis is strengthened because the proposed source need not produce a unique fragment. An impact releases a broad distribution of ejecta, so the relevant test is whether at least one block can occupy the required trajectory under realistic conditions. Giordano Bruno is therefore best treated as a plausible source, identified by combined physical and dynamical constraints. Its formation can generate fragments of an appropriate scale, and simulations permit some of those fragments to reach Earth-like resonant motion. Observations remain consistent with that pathway, while the exact birthplace of Kamoʻoalewa remains unconfirmed. At this level, the origin problem narrows from the whole Moon to a specific geological event. A relatively recent impact excavates lunar crust, accelerates fragments into space, and under rare conditions places one fragment onto a long-lived solar path close to Earth's. Giordano Bruno provides a coherent example of how that sequence can occur while remaining a hypothesis rather than an established history. The lunar interpretation is not the only explanation that fits Kamoʻoalewa's unusual spectrum. A study published in 2026 re-examines the available reflectance data and proposes that the asteroid may instead be related to ordinary chondrite material from the inner asteroid belt. In this interpretation, the apparent lunar resemblance results partly from intense space weathering acting on a fine-grained rocky surface, rather than from a direct origin on the Moon. The analysis focuses on the broad absorption band, near 1 micrometer. Its measured center is consistent with LL chondrites, a class of stony meteorites containing relatively low amounts of metallic iron and characteristic mixtures of olivine and pyroxene. LL chondrites are common reference materials in asteroid science because several known asteroids show similar mineral chemistry. The near-Earth asteroid Itokawa, which has been sampled directly by a spacecraft, is one important example. Fresh LL chondrite material does not reproduce every part of Kamoʻoalewa's spectrum. The difference becomes smaller when researchers experimentally alter powdered meteorite material to simulate prolonged space weathering. Laboratory irradiation can darken the grains, weaken mineral absorption features, and create a steeper red spectral slope. Highly weathered LL chondrite powder can therefore resemble the asteroid more closely than an unaltered sample. This result changes the interpretation of the red surface. Instead of treating strong redness mainly as evidence supporting lunar material, the newer work shows that an asteroid belt composition can develop a similar optical appearance under sufficient weathering. Grain size also matters. Fine powder interacts with light differently from a solid slab of the same rock. A surface dominated by small regolith particles can therefore produce a spectrum that differs substantially from exposed coherent stone. The proposed dynamical source lies in the inner main asteroid belt. One pathway involves the N6 secular resonance, a region where the slow rotation of an asteroid's orbit interacts with the gravitational influence of Saturn. This resonance can gradually increase orbital eccentricity and send small bodies away from the main belt toward near-Earth space. It is a well-established delivery route for rocky asteroids and meteorites. When models are constrained to an LL chondrite composition, the Flora asteroid family emerges as a likely source region. The Flora family is a large population of related rocky asteroids in the inner main belt. Its members occupy orbits near pathways that can feed material into near-Earth trajectories. Several Flora family objects also show mineral compositions compatible with LL chondrites, making the family a plausible physical as well as dynamical source. Model calculations in the 2026 study favor the Flora family over another possible source, the Nisa family, under the assumption that Kamoʻoalewa is an LL chondrite object. The result is statistical rather than historical. It does not trace the asteroid along a single recoverable path from one parent body. Instead, it estimates which source regions most efficiently produce objects with the measured orbit and assumed composition. The comparison with Itokawa adds another point of reference. Kamoʻoalewa can be interpreted as having broadly similar silicate chemistry but a more strongly weathered surface. That difference could reflect longer exposure, different grain sizes, different resurfacing histories, or combinations of these effects. Observations do not yet determine which process dominates. The competing interpretations therefore rest on the same limited light, but organize it differently. The lunar model emphasizes spectral resemblance to mature lunar material and the possibility of impact ejecta entering Earth co-orbital motion. The Flora model emphasizes LL chondrite, mineralogy, laboratory weathering, and established asteroid delivery resonances. Both use known physical processes. At this stage, Kamoʻoalewa's birthplace remains uncertain. Its orbit is measured with confidence and its surface is clearly rocky and strongly altered by space exposure. The available spectrum, however, can support more than one origin once weathering and grain texture are considered. The asteroid, therefore, remains a case in which improved models narrow the possibilities without yet producing a final identification of its source. This ambiguity illustrates a broader limit of remote spectroscopy. Similar minerals can acquire different appearances, while different starting materials can converge toward similar spectra after long exposure. Without direct samples, researchers must separate composition from weathering texture and thermal history using incomplete signals collected across great distance. The asteroid belt interpretation, therefore, remains a serious alternative rather than a minor exception. It demonstrates that a spectrum can point toward more than one plausible history when multiple natural processes shape the same surface. Kamoʻoalewa's origin can ultimately be tested more directly by examining material from the asteroid itself. China's Tianwen-2 mission, launched in 2025, is designed to collect samples from Kamoʻoalewa and return them to Earth in 2027. A returned sample can be studied with laboratory instruments far more sensitive than telescopes, allowing researchers to move from broad spectral resemblance to the chemistry, structure, and history preserved inside individual grains. The first measurements can determine the minerals present with much greater precision. Telescopes indicate silicate-rich material, but laboratory analysis can identify specific proportions of olivine pyroxene feldspar metal and other phases. Their chemical compositions can then be compared with lunar rocks, ordinary chondrite, meteorite samples returned from asteroid Itokawa, and other well-characterized materials. A close mineral match would strengthen one origin model while clear differences could weaken it. Elemental chemistry provides another layer of evidence. Lunar crustal rocks and LL chondrites form in different geological environments and preserve different distributions of major and trace elements. Tiny variations in iron, magnesium, calcium, aluminum, titanium, chromium, and other elements can reveal how the parent material formed and changed. Some grains may preserve chemical zoning created during crystallization, while others may record melting or shock produced by impacts. Isotopes offer an even finer comparison. Isotopes are forms of the same element containing different numbers of neutrons. Their relative abundances can act as natural tracers of planetary material and geological processing. Researchers can measure isotopic systems in individual grains and compare them with established lunar and meteorite data sets. Because Earth and the Moon share unusually similar values in several isotope systems, no single measurement necessarily provides a simple answer. A combination of isotopic, mineralogical, and chemical evidence is more informative than one marker alone. Microscopic textures can record the physical history of the rock. Lunar ejecta may contain fractures, shock features, impact, melt glass, or brecciated material produced by violent excavation from the Moon. Breccia is rock made from broken fragments joined together. Ordinary chondrite material can instead preserve structures associated with primitive asteroid matter, including characteristic mineral grains and textures produced during early solar system heating and later collisions. The exact structures present in Kamoʻoalewa can therefore help distinguish competing histories. The outer surfaces of grains can also preserve evidence of space weathering. Electron microscopes and other instruments can examine damaged rims, tiny metallic particles, glassy coatings, and other changes produced by solar wind and micrometeoroid impacts. These measurements can determine whether the asteroid's unusually red spectrum results from a strongly altered regolith and can test laboratory simulations used to reproduce its observed reflectance. Exposure history is another useful record. Cosmic rays produce measurable changes when they strike minerals in space. By studying products created during this exposure, researchers can estimate how long particular material has remained near an exposed surface or traveled as a small body. Such measurements may place limits on when Kamoʻoalewa separated from a larger parent and how its surface has been renewed. Not every grain needs to preserve the same history. A small asteroid can contain material excavated from different depths, altered during different impacts, or mixed by surface movement. Laboratory work therefore examines many particles rather than expecting one grain to represent the entire body. Differences among samples can reveal whether the asteroid is chemically uniform or assembled from varied fragments. Direct samples can also test the relationship between composition and orbital models. If the material is convincingly lunar, simulations of lunar ejecta become central to reconstructing its origin. If it closely resembles LL chondrites, delivery from the inner asteroid belt becomes more plausible. If the samples show unexpected properties, existing models will require revision without changing the well-measured fact of its present resonance with Earth. At the smallest scale, Kamoʻoalewa's history is stored in crystals. Isotopes, fractures, coatings, and microscopic grains. Remote observations narrow the possibilities, but laboratory measurements can separate effects that appear similar through a telescope. The asteroid's century-long companionship is explained by orbital dynamics. Its birthplace remains a material question, and the strongest evidence lies within the rock itself. Together, these measurements can connect present motion with ancient material history, while keeping firm conclusions limited to evidence actually preserved in returned samples. Kamoʻoalewa continues along its quiet path around the Sun, moving through the same broad orbital neighborhood as Earth while remaining physically separate from the planet it appears to accompany. Its motion is no longer mysterious in the basic, dynamical sense. The asteroid follows a solar orbit whose period closely matches Earth's year, and repeated gravitational interactions maintain the quasi-satellite pattern that has kept it associated with Earth across roughly a century. The deeper uncertainty belongs to its material history. Reflected sunlight reveals silicate minerals and a surface changed by long exposure to space. Those measurements are consistent with weathered lunar material, yet strongly altered ordinary chondrite material from the inner asteroid belt can produce similar spectral properties. Numerical models allow fragments from both broader histories to reach near-Earth space, although the pathways, probabilities, and starting conditions differ. For now, the small body carries both histories within the range allowed by observation. Its orbit is measured far more securely than its birthplace. The distinction is important. Scientific understanding does not require every uncertainty to disappear at once. Some features become clear through repeated positional measurements, others through spectroscopy, and still others require direct examination of physical material. Inside microscopic grains, mineral structures, isotopic ratios, impact damage, and weathered surfaces can preserve information that distant light cannot fully separate. Returned samples may eventually show which origin best matches the evidence, or they may reveal a more complicated history than either present model describes. Until then, Kamoʻoalewa remains a small rocky companion in Earth's orbital neighborhood, not bound to Earth, not motionless beside it, but moving through a stable gravitational rhythm around the Sun. Its long companionship arises from ordinary celestial mechanics, while the story of where the rock began remains written quietly within the material itself.